Alright, students, let's look at this question here, which was taken from the year 2017, paper 2, question 9, from the H2 math paper. So in this question here, question 9, on average, 8% of a certain brand of kitchen lights are faulty. The lights are sold in boxes of 12. So state in context, two assumptions needed for the number of faulty lights in a box to be well modeled by binomial distribution. Okay, so obviously there are four conditions needed for binomial distribution to be a good model, like to be well modeled by a binomial distribution. So the first one is the number of trials have to be the same throughout. But because now the boxes are all are told that it's all 12, so there's not really an assumption because you're told that. And the second one would be, it's binary, so meaning the outcome will be 2. Either you happen or you don't happen. In this case here, it's implied that it's either faulty or not faulty, right? The third one would be that each light, so probably the third one would be the probability of each light, right, being faulty is the same, okay? Or you can say it's constant at 5%. It's 8%, sorry. So this is 8%. Okay. 8%. Okay, great. This keyboard is a bit small, so it's very hard for me to type. Okay, great. So this is one. So help is the same or constant at 8%. Then the second assumption that is needed is actually the probability of a light being faulty is independent of another light being faulty. Okay, so this is obviously the two assumptions needed for it to be well modeled by a binomial distribution. Okay, let's look at the second part, which is part 2. Part 2, you assume now that the number of faulty lights in a box has a binomial distribution. So find the probability that a box of 12 of these kitchen lights contains at least one faulty light. So let 12 have at least one. So I'm just gonna name this basically X, right? Because it's only one mark, at least one faulty light. So I could just put X binomial. We have 12 lights in it, and every one would be 0.08. So the required probability would just be at least one faulty light. So probability of X at least 1. Okay, so in other words, this is 1 minus Px equals to 0. You want 1 minus 0.92 to the power of 12. Okay, so this is the answer for this question here. Key in calculator, you should get your answer. This is 12. It's 0.63233. Or you can just key in calculator. But the reason being is because this is just one mark. So I'm just they are just looking for the final answer. Okay. Let's look at the subsequent part 3. Part 3, you're told that the boxes are packed into cartons and each carton contains 20 boxes. Okay. This is part 3. And find the probability that each box in one randomly selected carton contains at least one faulty light. Okay. I think this is pretty okay. What we need is actually now for every one box, you have 20 a carton, right? You have 20 boxes, right? Every one box you have got the chances of having at least one faulty light would be this, right? So in other words, just Px at least one faulty light. So this is the probability distribution here. So each boxes would have this chance of have at least one. Now they ask to find the probability that each box in one randomly selected carton contains at least one faulty light. Each box in one randomly selected carton, that each box. Okay, so you want that every boxes have got faulty lights. So in this case here, you want P y equals to 20. Okay, so this is the case here. So key in calculator, you should be able to get answer. I'm going to key in calculator here. which is PDF 20, and try and put more SF here. This SF is 06. Why is binomial 20? Okay, so distribution, binomial PDF. Binomial PDF and trials is 20. Which is 0.63233. 0.63233. And we need this to be 20. 63233. And this is 20. Oh, there you go. This is the answer. Okay, so you need all 20 boxes to have. So this is 0.00 1.044 1.044 times 10 to the power minus 4. So this is 0.0001044. Yeah. Okay, so this is the chances that you have. So let's look at part 4. Part 4, find a probability that there are at least 2040 lights in a randomly selected carton. So meaning to say now that you don't want to just contain it into box, confine it into one box, right? You want it to be like a huge pot of lights, and you just mix everything up together. Okay, so I'm just going to do that quickly. So here we have 2040 lights. You have 12 boxes. One box you have 12 lights. One box you have 12 lights. And essentially 20, each carton contains 20. So one carton is 20 boxes. Okay. So, which also correspond to 20 times 12 lights. So this case here, what we get is actually just 240 lights. Okay, so out of these 240 lights, you want to find a probability there are at least 2040 lights in one randomly selected case. So you just lump everything together. So just define. So let K be the number of faulty lights out of one carton of 240 lights. Okay, so this is what I'm interested in. So I just let K be the number of faulty lights out of, so let me just put this as K, capital letter. Great. So once this is done, we have got K, which is actually binomial 240. Every one light which is faulty was 0.08, right? So this is 0.08. Great. So what we required probability would just be, we want at least 20 lights, faulty lights. So PK bigger than 20, right? So this is actually 1 minus PK, at most 19. So just take note of that. So what I'm going to do is actually just take 1 minus distribution CDF and 240 lights and 0.08% chance and 19. Okay, and 0.45833. The answer is actually 0.45833. Yeah. Okay, so this is the answer to this question here. This is how we do this part here. So let's look at the subsequent part 5. Part 5, you're told to explain why the answer in part 4 is greater than answer in part 3. So I think this is a typical question. This is not the first time they ask this question here. So let's see how we can explain this. So what's going on here is basically what they are asking is, if each boxes here has at least one faulty for case 3. And if each boxes will have at least one, so you add it up, you have more than 20 faulty lights. Okay, whereas for this one here, you also have more than 20 lights in excess. So the question now is, how come this is bigger than this, much bigger than this? Okay, so let's try to understand what's going on here. So let's break it down. I think the easiest way to understand is to just draw it out. So say we have got a carton, which is like how many boxes? A carton is actually 20 boxes, right? So 1, 2, 3, 4, 2, 3. Okay, let's say let's just go with this flow here. Okay, great. Then 1, 2, 3, 4, 1, 2, 3. Okay, so this is box 1 to box 2, box 3, box 4 to box 20, box 19, box 18. The question now is, how come if for case 3, if you have at least one and at least one, at least one, at least one, and at least one, at least one, at least one, that the probability will be different. Okay, that's what they're asking us, because this is actually more than at least 20 just in general, like because each boxes have at least one, right? So how come? But you realize that for case 3, you have to have all the boxes to be at least one, right? Whereas for this is case 3. Yeah. Case 4, what's going on in case 4 is you could have actually at least 5 here is fine. Then after that, at least 15 here, and 0, 0, 0, 0, 0. This case 4 would actually take this case here, and after which, obviously, if you do not like this, case 4 would also take at least 2, at least 2, at least 15. I'm just getting anything that I'm thinking like that. Okay, at least 1, 0, 2. So all these would actually be part of case 4, because case 4 doesn't restrict it to a box. Case 3 restrict to a box. Each box must have at least one, whereas case 4 is in totality, in the whole, like in the whole 240 likes, right? I just need to have like 20. So you realize that actually case 4 can also take case 3 in. So case 3 would also take it in as such. Okay, so this is case 3. This is 1. 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 So case 4 could also take case 3 in. So essentially, what you can write for part 5 is that events in case 3 is the subset of events in case 4. Okay, so that's all. It's 1 mark, so you just have to explain as such. Just say that it's a subset. Alright? So let's look at part 6 of this question. You're told that the manufacturer introduces a quick test to check if the lights are faulty. The lights are identified as faulty, are discarded. If the light is faulty, there's 95% chance the quick test will correctly identify the light as faulty. If the light is not faulty, there's a 6% chance that you will incorrectly identify the light as faulty. Okay, let's see how we can do this properly. So this is part 6. I think first of all, we need to define the events first. So let F be the event where the light is faulty. I will let C be the event where the test correctly identify the state of lights. Okay, so of a light. So that's what we're gonna do. So this case here, you're told that the light is faulty. If the light is faulty, so probability if the light is faulty, given that if it's faulty, there's a 95% chance that the quick test will identify it correctly. So this is 95% chance. So this is 0.95. Okay. then there's a 6% chance that the quick test will incorrectly identify the light. So this would be incorrectly identify the light as faulty if the light is not faulty. So if the light is not faulty, this is there's a 6% chance. Okay, great. So this is how you do it. So find the probability that a light identified as faulty is not faulty. So essentially, right, you have already identified it as faulty by the quick test. So in other words, you have already identified as faulty. This is one, and after which you need to and also you need not faulty. Quick test is not faulty, so this is not faulty. Okay, it may seem like you could express this in terms of CNF, but it's not. But I'll try and explain later. So we're gonna look and try and draw a tree diagram out. I think this tree diagram should be quite quick to draw. So you have got the first thing. This is given that F happens first, so it has F have to come first. F has to come first. F prime, then C prime, C prime here. So this case here, what we get is faulty. Faulty would be, for a light to be faulty on average is 8%, so 0.08. This is 0.992, right? Then after which you have got the correct, which is 0.95, which is this case here. Then this is 0.05. This case here will be 0.06, and this will be 0.94. That's pretty okay. Now, I'm gonna try and see how do we solve this conditional probability here. You want it to be identified as faulty for the bottom one. So identifying as faulty would be this case here. So faulty and correctly identified. And if you're not correct, this will be identified as faulty as well. Right. So if you're not faulty and you get a wrong result, you will identify as faulty as well. So this is identified as faulty as this, because this is not faulty. So if it's wrong test, then it's identified as faulty. It's interpreting it, which is the tough one, I think, for this case here. So this would be 0.08 times 0.95 plus 0.92 times 0.06. Okay. Then after which you think about not faulty and identify as faulty, which is this branch. Out of these two branches, this is the only branch which you are talking about not faulty, right? Sorry, not faulty is this one, F prime. So 0.92 times 0.06. Alright, so key in calculator, we get answer 0.92 times 0.06. Then after which you have 0.08 times 0.95 plus 0.92 times 0.06. Okay, so this case here would be 69 over 164. Okay, so this is how you do this question here proficiently. Any questions? Yeah, please do let me know, okay? Let's look at part 7. So 7 would says that identify if the test correctly identifies the state of the light, right? Correctly identify. So if you look at this triangle, this tree diagram here, the one that which correctly identify would be faulty and correct, and non-faulty and correct here. Okay, so it would be just required probability okay, it will just be faulty and correct, just be correct about it. So this is 0.08 multiplied with 0.95 plus 0.92 times 0.94. Okay, so this case here, what we can get is actually 0.08 times 0.95 plus 0.92 times 0.94, which is actually 588 over 625. Okay, Let's look at the last part of the question. So the last part of the question, you are told to discuss briefly whether the quick test is worthwhile. Quick test is worthwhile. We try and understand whether the part 6 and part 6 and part 7, part 6 and 7, whether it makes sense. So for part 6, 69 over 164, let's just quickly calculate the this is roughly equals to 42.07%. Okay, this is roughly equals to 58.625%. This is about 94.08%. Now take note, this is correctly identified. Is this correct or wrong? And you know that this is the chances where the like is 40 is 8%, so just bear in mind. But let's try and make sense of part 6 first. 42.07, this is a very high number, meaning if you identify as 40, if it's faulty, in the back of 40 identified, let's say if you, after you run the test, in the back of identified 40 bags, you have about 42% of it which is actually working fine. That is not good, man. Which is actually working fine. Okay, this is how you interpret conditional probability. So you it's obviously not a good test, right? Because from you can just quickly write this down per part. Also from part VI, out of all the out of all the likes which are identified as faulty, we have about 42.1% of likes which are working correctly. Okay, yeah, it's too high. 42% is too high. So which is a very high margin of error. Okay, moreover, like you still need time to run the test, right? So I don't think is really like useful. So I don't think it's worthwhile. So hence the quick test is not worthwhile. Okay, so this is how you understand the question in context of the question, right? So that's how we do this question here proficiently. Any questions or comments, please do let us know. Keep practicing, and I'll see you in the next question.